Okay, good, great, thank you. We're very happy to have Junwu here from Perimeter to tell us about a new pulsar. What? Yes. I don't remember how to do that at this point.
All right, as Seth figured out the technical details. Thank you to everyone who comes, and thank you for inviting me to give a talk. Yeah, today I'll be telling you some things that I have been doing with, well, started, well, it will take some time, so I can give you a longer introduction. We started when Will and I both moved to Perimeter and postdoc in 2017. And it took us 5 years to actually work out the problem with Marshall initially, and also later with 3 more people on the team. Niels is a PhD student at Perimeter. He's graduating this year. He's going to Princeton. He's a student of Will East. And then Christina and Daniel both postdoc at PI. We'll show you what we did. Okay, so as all talks, I will start with the conclusion. So today I'll be telling you about a new phenomena which we discovered, which requires 2 things. The first thing that we know they exist, which are spinning black holes in our universe, and we know they exist because light will spin them as merger product. The second ingredients we need are these hypothetical particles called photon. When we have these 2 ingredients, what I will show you is through what is known as the vector superradiance, we'll produce a cloud of that photon around the spinning black hole, and which later through kinetic mixing produce a lot of charged particles around this spinning black hole, and the system behaves roughly like a pulsar. We'll show you the similarities and differences between our system and a real pulsar based on neutron stars. And then what are the observational signatures, which will be this plot here. So that will be the plan of the talk. Most of the talk, I will be talking about the complicated electrodynamics inside the cloud, superradiance cloud. But to start with, I will give you a short introduction to the black hole superradiance process, and then what are these particles called. Okay, let's start. Okay, so first let me give you a quick introduction to superradiance. So the superradiance process, the simple example is basically a rotating cylinder with frictional surfaces. So if I take a ping pong ball and I throw it on a cylinder which is rotating, on the surface there's friction, then if the cylinder is rotating slower, then the angular velocity of this little ping pong ball, then the ping pong ball will be slowed down. Well, if the cylinder is rotating very fast, the ping pong ball will come in and come out with more momentum. So this is the simplest example of superradiance. It points to 2 conditions. The first condition is that the surface has friction. The second condition is that the cylinder is rotating faster than the ping pong ball coming in. When you have satisfied these 2 conditions, then this ping pong ball will come out with a larger velocity. So similarly, this process can happen for black holes as well. Now, instead of sending in a ball, I'm sending a wave. So if I'm sending a wave which has its own angular frequency and incidenting on a black hole which is rotating, then if the black hole is rotating very fast, then this wave will scatter with the black hole and come out with a larger amplitude. So this can be seen is this video, which is a simulation that we released Huang. What he did is he's sending a wave after it scatters black hole, it comes out with a much larger amplitude. So people have known this for a long time, and in 2010, these 2 people, Mina and Sergey, realized that if instead of massless particles, which are these photons or gravitational wave, they scatter once and leave the system, we have massive particles. Then the gravitational potential GM mu would be able to trap this non-relativistic massive particle wave, and then this wave will be continuously scattering with the black hole when it is trapped in the gravitational potential, continuously extracting the angular momentum from the black hole, and continuously amplify its amplitude while in orbit around the black hole. So this can be seen in this video here, where you see this massive wave, which is bounded by the black hole, increasing in amplitude as a function of time.
It's special to bosons, right? Or
Yeah, it will be bosons. Yeah.
they won't happen for fermions, or
Yeah, because of Pauli exclusion, it won't. I would say that in the next slide. But okay, yeah. That's, thank you for the question. So when you see this this type of bound state, you can ask like, and it seems to have a regular shape. We can ask like, what are the wave functions of this bound state? So to do this computation, basically what we are solving is the Klein-Gordon equation in this gravitational potential. The gravitational potential is very similar to the electric potential around in an atom. So here, instead of the phi structure constant, we have GM of the black hole, the size of the black hole over the Compton wavelength of the particle. So GM mu is the new phi structure constant for this gravitational atom. So with this potential and something like a Klein-Gordon equation, we can solve for the wave functions around the black hole. And as the question, we know, like if we scatter with bosons instead of fermions, now we don't have Pauli exclusion, which tells me like each energy level can only be one particle. Now instead, if we have boson waves which continue to scatter with the black hole, then this boson waves will be exponentially growing until it reaches some like a ginormous number in a very short amount. So the important number to remember is this alpha here, which is this combination, and roughly it is a number that is order 1 smaller than 1, maybe like 10 minus 2. Okay. So with these things, we can solve for the wave function, and here we are interested in a vector field. So in this video here, I'm plotting you a vector as a function of time. So the level I'm plotting here is the fastest superradiativity level. It is S wave state, which has L equal to 0, J equal to 1 because S equal to 1, and then M equal to 1, so that it can be superradiative. So the wave function are basically shown with this arrow here. The arrow gives you the direction of the A vector. So at any time, all of these A vector are parallel to each other. Well, it's bigger like in the center and smaller on the side. And as a function of time, these arrows all rotate together around the spinning of the black hole. And the rotation period is 2 pi over mu, where mu is the mass of the particle. Okay. So that's how the cloud look like. Of course, when you have this changing time-dependent energy density in this gravitational wave, and this is showing this simulation here, where you see like the cloud rotating and gravitational wave being emitted in this rings here. Okay, so the gravitational wave emission will be the for most of the talk, and actually for all of the parameter space we are interested in, will be the dominant energy loss mechanism for this superradiance cloud, and that sets the lifetime of the cloud. So that's all I want to say about superradiance, and let me give you a short summary of this part. So there are a few numbers that we want to remember. The first thing is that the energy density in the cloud is ginormous. It can go up to 20 MeV everything to the 4. So this is a huge energy density that are comparable even to the energy density of a neutron star. So there are 3 length scales in the problem, which are important, and I'm drawing you here too, so that you can always look at it if you want afterwards. So, and all of these length scales are summarized in this plot here, where I have 3 length scales. The first one is the GM, which is the size of a black hole. Then we have 1 over mu, which is equal to 1 over omega, the rotation frequency of the black hole is superradiance sector. So this 1 over mu scale is a little bit larger than GM. And then like there's the cloud size, which is basically the Bohr radius of the cloud, which is 1/alpha mu, and that is even bigger than 1/. So these length scales will be important later, and I just want to stare at this and remember. Okay. So apart from length scales, we have time scales. There are 3 time scales as well. So the first one is the rotation period, which is basically 1/mu. There is the superradiance rate, which is much slower. It scales as often to the 6, which tells you how fast this cloud grows after the black hole is born. And then there's the cloud decay rate, which is even longer time scale, which tells you after the cloud has been produced, how long does it dissipate away through gravitational wavelength.
So you got confused about mu, then
Yeah.
is the rotation. So
Uh,
is the mass of the
Mass of the boson is mu.
you ask for it to be close to the
No, like the superradiance condition.
is that separation?
After like a superradiance has got to the point that where like no more particle is produced, omega is equal
I see.
to mu.
I see.
So it's not a
So
tuned,
that
it's just
is
like automatic.
Automatically, dynamically tuned
Yeah.
to that. Okay, very good. Thank you.
Okay. More questions? No. Okay, then let's switch to that. So that photon is a hypothetical particle, which I've been searching for a long time. The action that governs its dynamics is basically this one. It's like a photon, but it has a mass, and it couples to us through the kinetics parameters. So throughout the talk, I will be actually using this action, which is not always true in general systems, but for our system, it describes all the essential physics. So that's why we'll stick to this one, because it's simpler to explain what is going on. So the parameter space of the dark photon is basically the mass of the particle and the kinetic mixing parameter epsilon, which tells you how much weaker this dark photon is coupling to us, the Snell amount of current compared to a real photon. So throughout the talk, we'll be interested in a parameter space that is roughly here, where the right-hand side is basically cut off by when we don't have black holes anymore. So 10⁻⁻10 -11 is inverse of the radius of stellar mass black hole, and then like it can all the way go to the left, and it will be this region here for epsilons all the way down to 10⁻10. So this is the parameter space we'll be interested in, and we'll see what happens in this region. Okay. So that's all I was saying for that photon. Now I want to put on the back. Okay. So what I will show you next is basically what are the dynamics that happens inside this black hole superradiance cloud, that photon superradiance cloud, when I have a kinetic mixing between the photon and the dark. So in the next 20-30 minutes, I will be explaining to you what these 4 panels mean. The first one is simple, it's just a spinning black hole. So we'll start from the second. Okay, so here, what I wanted to tell you are basically how does the electromagnetic field coming from the dark photon superradiance look like. So earlier I showed you the A vector as a function of position and time, if you still remember. Now with this A vector, I can compute the electric field, dark electromagnetic field, and the Snell model, the electromagnetic field that the charged particles, which are at orders. So this is how the field look like. So the electric field are still mostly parallel to each other because most of the contribution coming from dt A vector. And it's basically A vector rotated by 90 degrees. It's not totally in parallel because there's this additional term, which is of order alpha squared smaller than the first. So basically the electric field have this type of shape, and they are rotating around with the period. You can also compute in the magnetic field, which looks like this. It's basically the curl of A vector, which is pointing in a single direction. So it's like the magnetic field around the current. So that's why it has this shape. As the cloud rotates, both of these things rotate around the black hole. Okay. So that's the shape. What about their strengths? So here I put it back the epsilon parameter to characterize how much weaker it couples to us. And if you think about these fields as the field that the electron actually sees, then we are talking about something that is over order 10 to the 10, 10 to the 11 Gauss. Over a size that can be the cloud size, which is 150 kilometer for a black hole with a solar mass. So if we have something like 10 to 100 solar masses, then we are talking about a volume that is much, much bigger than a neutron star, with the field strengths that are comparable to the neutron star field strengths. That's how we see that this object, even if it is really, really far away, maybe we'll be able to see signatures from it, like ours. So for particle physicists who, like me, a skill that gives you some sense of like how dramatic things can be happening in this cloud is by combining this epsilon e prime and RC. That's basically the amount of acceleration you can get from the electric field, and that can get particles to 10 to the 10 GeV if like the system actually vacuum. The system, as you will see, this cannot be the case. It gives you a sense of the energy that we're talking about. Okay. All right. So now we'll talk about what are the processes that can be happening in this cloud. So which leads to some sort of new equilibrium. So the processes that matters the most are basically the synchrotron emission, which basically comes from the fact that these charged particles are moving very fast with a high boost in electric field, which is rotating. And gets acceleration perpendicular to the charged particle, the direction the charged particle is moving at, which gives you photon emissions. The second process is the fact that these photons, when they travel through the cloud, they will scatter with the electric or the magnetic field and produce charged particle pairs. So when you have these two processes, what you will have is even if you start with one charged particle, it gets in, it radiates these synchrotron photons, which split into charged particle pairs, and these charged particle pairs will again emit more and more photons, which gives you more and more charged particle pairs, and this goes into a cascade. Right? So even if we start with one charged particle, in a very short amount of time, you are going to create a large charge density, and the system will reach a new equilibrium. I'll give you more description of this new equilibrium in a bit, but let's first look at the parameter space where this process happens. So, so this is the plot of the parameter space again of that photon and the mass on the x-axis and the epsilon on the y-axis. What you see is that for a 10 solar mass black hole, this is a region where these pair production processes are efficient. Well, for a 100 solar mass black hole, it's basically moved to the left by 1 magnitude. So now we see that even for epsilon that is of order 10 minus 11, I can be producing these charged particles around the black hole. And then the question is like what type of equilibrium reaches and how fast it reaches. So the time scale.
It's not even, no, it is, I need very light particles.
Huh?
I need very small mu.
Yeah, yeah. I need a mu which are comparable to the black hole.
Yeah.
Yeah. So, so the time scale is shown on the plot on the right, where we compare the plasma production time scale to the superradiance time scale. So these numbers are all much smaller than 1. What it means is that as long as the superradiance cloud has reached some critical electromagnetic field, where this plasma particle production process start, then these particle production processes are much, much faster than the rate that the electric field is changing over time. Okay? So what it means is that quickly after it reaches some critical field, I produce enough particles such that the system reaches some quasi-equilibrium, and then afterwards the dark electromagnetic field will continue to grow through the superradiance process, while the charged particles will grow adiabatically with the growing superradiance cloud. So that gives you a sense of when does the this instability happen, and like when does this transient happen, and it tells you like actually like the transient didn't contribute very much to observation of signatures. Okay, so I still haven't told you like how does the equilibrium how we reach the equilibrium. And to talk about that, I will use an analogy with something that you know.
So sorry, just to make sure that
Yeah.
the picture is that you start building up this crowd and then
Yeah.
in the meantime, these things are happening.
Yeah.
And then because they are fast.
Yeah.
And that does it, if it's very fast, that is do you still eventually reach?
Yeah, so like what the charge particle do, as I will show you, is they spring out the part which couples to the electron. Well, the dark electric field will continue to grow.
Okay.
You will see like after I describe
But
this.
they do take energy away from the.
They take away, they take energy away like very, very slowly. They don't really back react on the growth of this cloud, but they short out the electric field part, which the electrons see. Okay, we'll show it. Okay, so right. So next I'll show you basically how Cascade ends. Using analogy with the thunderstorm. So a thunderstorm, as you know, is starts when you create an electric field between the cloud, well, real clouds, and the ground, right, the Earth. Okay, so once I create this potential difference, there are electric field between the two. When the electric field become large enough, there is a breakdown, and the current start flowing through the thunderstrike. Okay, the current brings positive charge particles to the cloud and negative charge particle to the ground, and these charge particles will set up their own electric field, such that it cancels the original electric field you started. Right, so that's the picture. When this equality is reached, of course, there's no electric field in the middle and no charge flowing again, and then like this cascade has stopped. Okay, of course, like in real ENM, like there's no difference between this electric field or that electric field. They all created by charged particles. But in the case of the Superradiance cloud, this is not the case, because the original electric field you set up come from the dark photon at order epsilon. While the purple charge particles, they create an electric field, which are actually coming from charge particles, and they set up their own electric field that cancels this field that you set up with the Superradiance. Okay, so now at this point, the electrons in the Superradiance cloud do not feel a force anymore, and then like this cascade gets to the end. Okay, so of course we know that the Superradiance cloud is gravitationally trapped by the black hole, so they don't go away. But the charge particles, they are separated, so they look like a dipole. And I can take away the Superradiance cloud, which doesn't radiate. What I'm left with is basically electric dipole, which is rotating around the spin axis of the black hole, as the Superradiance cloud is rotating around the spin axis of the black hole. Okay. So this picture we know, because it is very similar to a pulsar. So there are many nice artistic view of the pulsar, but for me, as a serious, a pulsar is basically a magnetic dipole moment, which is rotating around the spin axis.
So in this environment where you've got both these electric fields and a plasma of standard model particles, do you ever have to worry about there being a plasma mass that affects how you think about the dark photon?
Yes, so that's the basis question. The same, right. So I will answer your question. So basically, like naively, you would say like the plasma mass is bigger than the mu, so like the coupling is suppressed. That discussion is based on the requirements that the cloud or the dark photon is a small perturbation to the system, which is not true here. In this case, the dark photon cloud has much more energy than the epsilon squared of it, right? Which are the electromagnetic field, which are still way bigger than the energy density of the standard model charge particles that is in the system. So in that limit, like the parameter which better describe this behavior of the system is the conductivity parameter. And I will show you how the conductivity parameter change like this behavior. But the quick answer is that you do not suffer the same mu squared over omega plasma squared suppression.
Thanks.
Okay. It's a detail, but that is related to the basis question, like we talked about I tried to not avoid earlier, but let's coming back to this picture of this magnetic dipole, which is rotating around the spin axis of the neutron star, right? And that is very similar to our system, which is electric dipole, which is rotating around the spin axis of the black hole, right? Of course, electromagnetic radiation doesn't really discriminate the two. That's how we expect the system that we have behaves very much like a pulsar. Okay, and I saw as the series, I thought we are almost done, but then we realized like it's not the case, and for that we need to come back to this picture. So this is a real pulsar. A real pulsar has the magnetic dipole moment on the neutron star, while the light cylinder radius, which is 1 over the rotation frequency of the neutron star, is much bigger. Or in other words, omega times our neutron star, where the magnetic dipole is located, is smaller than 1. For our system, it's not the case. The electric dipole extends through the superradiance cloud, which is bigger than light cylinder radius, which is 1 over omega, which is equal to 1 over. Right? So instead of this combination being less than 1, I have omega times RC, which is much bigger than 1 for alpha that is smaller. So what it means is that in order for these charged particles to keep up with the rotating cloud, since need to be moving at a speed that is much larger than the speed of light, which certainly is not the case. And that's when our analytical understanding failed. And now we need to turn to simulations to see how this system actually behaves. So that will be the last figure. Okay. All right. Any questions about the periodicity part?
Is it obvious that they should be distributed spherically like this? Because I mean, you're filling up orbitals through superradiance that have non-trivial angular momentum. So
The fastest superradiance level is the S level. That's why I like it spherical.
So for such a strong magnetic field, you don't have to worry about like the higher order corrections in your action.
From what? From like
mixing.
From like electron loops, you mean?
Yeah.
No, like no, and the reason is like physical electrons are almost more important than electron loops. We have physical electrons in there, which has a current. Right? So these are like changing the system like much more than like the loop suppressed. Okay, so simulation. So to start with, let me catch up everybody to what people are actually doing in these simulations. So let me just start with a description of like what we are doing, like we are simulating pulsar magnetic. So we are solving is basically the Maxwell equation, right? Like around the neutron star. Certainly, like I cannot really just solve this because I don't know what Sj is. So I need a prescription to tell me how does the current depend on the background electromagnetic field. And such a relation is known as the Ohm's law, basically, which tells you how does the current depend on the electric field or the magnetic field, which are pushing on the charged particles. So in the case of a metal, the Ohm's law is J equals sigma E, right? Everybody knows. The E is the force, and then the J is the current which are generated because of this force. Similarly, for pulsars, of course, like the system is mostly magnetic field instead of electric field. So I need to use the Lorentz force instead of just the electrostatic force. And with this new current, I can solve this Maxwell equation for E and B. And in particular, people solve this in what is known as the force-free limit, which is basically the limit where I take this conductivity parameter to infinity. At that point, like this combination equal to 0, the Lorentz force is equal to 0 and has the negative force-free limit. Okay, so we need to do something similar. So we need to but like now we need to include like all the dynamics of the dark photon field. So the real thing that we do is actually much more complicated than this, but this just gives you the sense of like what we need to add, what are the physical ingredients we need to add. So the first thing is that instead of one set of Maxwell equations, I have two sets of Maxwell equations. Also another one for the dark photon. And then for the Ohm's law, now not only the electric field, which is pushing on the charged particles, the dark electric field and magnetic field are doing that too. That's why like we need to extend the Ohm's law to include both. As I said, the dark electromagnetic field is not really feeding the back reaction coming from this charged particle cloud, because they contain too little energy density. I can use this roughly as the background equation solution, and then like I can solve for the electromagnetic field as a result of this background dark photon electromagnetic field and the charged plasma, which is in. So in our case, we can actually not really solve it in the sigma going to infinity limit. I will show you why. So only solving it in the limits where I'm taking sigma to be larger and larger compared to this. As we will see, like these dynamics which emerge as I take this limit are important for the observation of sigma. Yeah.
What's your determining sigma value?
So sigma in reality is some number which is can be like a 10 to the 10-ish. So it's a huge number for this plasma. It's really, really good conductor. Of course, we cannot really do that, right? Because the 1 over sigma is a length scale in the simulation. So so the idea is like I take sigma to be bigger and bigger until I get like a energy output dissipation which has saturated. So that's basically like the idea of like doing this prescription that I will show you. Okay. Good. All right. So we did the simulation, and this is the result. Okay. So the first thing that I want to show you is the charge dipole in this video here. So you do see a dipole between dipole here. So the blue is the positive charge and the red is the negative charge. So you see like a dipole pointing in this direction. But as I was telling you earlier, of course, the charged particles cannot really move at the speed of light, which is why like there is a significant lag the further away you are coming from the back. So the other thing that you see in this figure are these small islands, right? It's not a numerical issues. They are actually real physics. Okay. So and the physics is better shown in this figure here, where I'm plotting the magnetic field strength as a function of location for a larger and larger signal. Okay. So what you see is that there are these structures which emerge when I make the conductivity parameter bigger and bigger. So what are these? What you are seeing here is turbulence. It's very analogous to turbulence that you see in fluid dynamics. So so this is an Niagara Falls, right? I'm from Canada, so this is where like you see laminar flow on top and the turbulent flow on the bottom. So whether a fluid is turbulent or not is determined by what is known as the Reynolds number, right? If the velocity of the flow is fast, if the extent of the flow is large, and if the fluid is not very viscous, then the Reynolds number will be large, and the system will be turbulent, right? The fluid. So similarly, we can ask what are the equational motions of the magnetic field inside this magnetoplasma. And I didn't show you the equation, but like it is analogous to the Navier-Stokes equation, from which you can actually define a parameter called a magnetic Reynolds number, which again depends on three parameters. The first one is the conductivity of the plasma. The second one is the differential velocity between the magnetic field lines, and the third one is the extent of this plasma. Okay. So again, when you have larger conductivity, larger flow speed, and very good extent of the object, this Reynolds number is large. and the system goes turbulent. So it took us a long time to figure it out, but this is what you're actually seeing in these figures, right? So as you increase the sigma conductivity parameter, first you are seeing these turbulent activities emerging from the outside, and as you continuously increase sigma parameter, like these activities goes more and more closer to the inside until it happens everywhere in the Superradiance cloud. And that's why we stop at the sigma equal to 20, because it has saturated the point to the point where like everybody everywhere like in the cloud, we are seeing like a turbulent energy dissipation. And that's what we are seeing here in this video, where there are energy dissipated, mostly in the region where like the color is red, and these regions like move around and has this filament like structures, which looks very much like the structures I was showing you in the previous slide. So we think like these two things are related, and that's why we zoomed in to a region where like the energy output is large. That's what we are doing here. So in particular, let's look at this figure here. So the red region, which are this region here, is where like the energy dissipation is maximized in this region, which coincide with the region where magnetic field lines are connecting with each other. So these are the regions where I have two magnetic field line bundles which are crossing each other, forming loops, and those are the regions where the system goes turbulent and the energy is dissipated into the charged plasma. So that's how we show that these two things are related. The magnetic field line reconnection processes are actually the dominant process where we get energy dissipation. Okay, so so with this in mind, we can compute the emission power integrated over the whole of space, and the plot, the line you want to look at is this one here, where we show that this luminosity actually saturated to a point where we expect. So the black solid line would be the line corresponding to when the energy output from flow, which is totally nonlinear, which you see like the simulation details from. So combining all of these, we got to a number, which is probably the most important number for this talk. That is the luminosity coming from this object can be ordered 10 to the 43 per second for epsilon parameter of 10⁻⁷ around a solar mass black hole, and this is 10 order of magnitude larger, brighter than the sun. Okay, so we can put this in this figure here. Again, like of the dark photon parameter space. So we see that for a large range of the parameter space, we can get luminosities larger than 10 to the 39 per second, which are larger than the Eddington luminosity around these black holes. Okay, so that gives us the confidence that even if these objects are really, really far away, we'll be able to see them.
It is actually pulsar or just continuous source?
Huh?
It is actually pulsar if the source is turbulence. Yes,
Yeah,
that's
so
like
like yeah, that's the next slide.
Okay.
So what about periodicity? So we see a lot of like processes which gives you periodic emissions, and we actually see like the emission power to be always periodic. But like we in the simulations, but I think like more simulations to be done because to actually like make it 100% complete or like bulletproof, because the simulation that we run doesn't allow for energy dissipated to affect the thermodynamics like in that region. So if we run a PIC simulation or something like that and see the same periodicity from the system, then I think like we are 100% sure that the emission is periodic. But coming back to the periodicity, we see like a periodic emissions with a period of 2 pi over mu, as we expect. And this period is independent of alpha parameter, which
So just a down question.
Yeah.
This is different from the actual pulsar, the one that kind of signal you see is different from the actual pulsar.
The signal can be similar. The luminosity is much bigger.
There's no way pulsar can give this even.
Huh?
There's no way pulsar can give you this kind of luminosity.
Yeah. Right, cannot. Because and the main reason is because our object is much bigger than pulsar.
Right.
Yeah.
You have to measure their distance pretty well.
Yes, and I would go back to this where we talk about auxiliary signatures. But to conclude this part, I will give a quick description of the spectrum. So the spectrum coming from this object is mainly determined by this parameters here, which is the average magnetic field strength, and which can tell you about what is the peak frequency of the emission. The peak frequency for us is around 10 to 100 keV, and it will be some the peak frequency is in the range of X-rays to gamma rays. So that's why we'll
Sorry, where is mu here? So then
no this is
the dependence on the mass.
oh no so here I'm writing in terms of m and alpha. So mu is equal to gm alpha over gm. So it's 10 minus 12-ish. Yeah. Okay. So a summary of this part, we talked about the pulsar dynamics, the energy dissipation mechanism, and the peak luminosity, which can be really, really bright. Okay, so in the last 15 minutes, I will be telling you about how we can look for this object. So, and the way that we look for this object is by using analogies with pulsars and magnetars. So there are two such strategies. Either we start from gravitational wave and try to see if we can find a pulsar, or we start with a pulsar, we tag this pulsar and see if it can be emitting gravitational wave and be actually a fake pulsar instead of a real pulsar coming from the transistors. So I will be describing both of these cases separately. So the first one is more better for larger alpha, and the latter one is better for smaller. Okay. So for the first case, what we are trying to do are advanced LIGO follow-ups. So advanced LIGO, as we know, produce spinning black holes, boost mass, and the final spin that we know to a very good precision. So if there are these particles around, then they will create a cloud within a very short amount of time. And this is shown to you in this plot here, where you see the luminosity just grows very rapidly within some Superradiance time. And then over a much longer time scale, it decays away, where the time scale is set by the gravitational wave emission. So the important thing here is that the signal period, the signal rise time and the signal decay time depend on only one single parameter, and that parameter is alpha. And so once I measure any of these, knowing the black hole mass, I will be able to predict everything else. And so if you see a pulsar which starts shining after, a black hole merger event, you see in LIGO, and I can predict to you when it will stop. And that's how we can think of one way that we can think of distinguishing the object that we see with the real world. So here, in this plot, I'm showing you some of the current observation that we have. So for 3 different black hole merger events, with instruments that we already have, like Swift and Chandra, this is roughly the range of parameter space we can cover with accurate measurement for these black hole merger events. And then if we assume 10⁻⁴ component going to radial, like a real pulsar does, then we might be able to cover a wider range of parameter space. So in the future, there are already X-ray telescope already in orbit. Actually, this is using the sensitivity curve of zeta. If we demand that we have 1 event per year seen in an X-ray telescope, then this is a range that we can cover. I don't know why like the color is not showing up correctly,
We can see.
but everywhere like above this. So everywhere over there, like we will expect like a event per year, and then like if we are looking for over 10 years, then we'll be able to see like the 10 of these objects. And then like you can do another interesting quad check, because all these time scales, once we know the black hole mass of each single one of them, these time scales will scale uniquely with the black hole mass. And if they all line up in a line that we predict, then we know like these are all the same objects coming from the same superradiance, coming from the superradiance of the same particle. Okay. So the second type of search is to ask if some of the pulsars that we already see in the universe are actually a black hole pulsar. So this can allow us to go to much smaller alpha and much smaller mu, because these anomalous pulsars are usually like closer to us. So there are two ways we can select through the pulsar catalog for the events that we want. The first way that we can select is that F dot for all like black hole pulsars would be positive instead of normal pulsars, which are usually negative. So the second way that we can search is that all of these pulsars would have the same period that are set by the mass of the particle. So that is how we select all these pulsars, and then we can be targeting the gravitational wave emissions coming from this black hole superradiance cloud, which are usually much stronger than the gravitational wave that will come if the pulsar is actually coming from neutron star. So this is showing this figure here. So these are all the pulsars that we selected. As you can see, many of them are already excluded, which are these solid triangles, while the empty triangles are not. So this curve and the great Schroeder region is excluded by searching for gravitational, like just stochastic gravitational background. This solid line is what you can do if you do a targeted continuous gravitational search on a pulsar where you know where it is. So you can see that all of these will be able to be covered by the search if you do a dedicated search as compared to a gravitational stochastic search. So, and the reason we can do this search is because when we compare the string of the black hole of gravitational wave coming from a black hole pulsar as compared to a neutron star one, if we fix the frequency and the F dot, the string is usually at least 4 order magnitude bigger than the ones that are coming from the neutron star. And this is basically what I'm showing you in this plot here, where like the blue and the red are actually the same object, and the red are if we assume it's coming from a black hole, whereas the blue is what if we assume it's a black hole. Yes.
And that's a basic question, why we must see gravitational wave together with the both, like.
Yeah, because like if I have this superradiance cloud and it is rotating, it always emits gravitational wave. Right.
Yes.
Independent of epsilon.
Yeah.
And the gravitational wave is what generates this F dot. So once I know F and F dot, I know how much amplitude in gravitational wave it is emitting. And that's why like I can predict what it is like on this point.
Yeah, I understand, but just by looking at the pulse, like light emit X-ray emission, you cannot.
No, then like in that case I cannot, but like LIGO can see the gravitational wave that will be emitted from these pulsars. So if LIGO look at this pulsar and didn't see any gravitational wave, it's a neutron star. Otherwise, maybe it's a black hole pulsar. Make sense?
Yeah.
All right, so that's pretty much all I want to say. Let me conclude with this this plot here. So there are two such strategies that we propose to look for this black hole pulsar or the Superradiance pulsar, where the purple line shows you the region above which I can cover with a merger follow up as LIGO, while the green box are the region where we can probe by looking for the anomalous gravitational wave emission from a pulsar that we already know. So yeah, that's all I want to say. This is a conclusion again. We see how with the black hole superradiance and photon, we can create these vector superradiance cloud around the black hole, which produce charged particle densities with a dipole moment, leading to complicated electrodynamics, especially turbulence, which dominates the energy dissipation from the system, and which we can see even if they are at cosmological distances. And that's all I want to say. That's it. Thank you.
So is there something similar for the axion?
No, like there is nothing similar for the axion. The reason is like the axion, the field that you are actually coupled to is gradient of A, which and the gradient is very small. So the field strength is very small for the axion.
Axion doesn't generate new.
And axion in principle itself doesn't have a direction. So you are not really gaining the acceleration over a long distance anymore in axion cloud. So the similar dynamics doesn't happen for axion.
If you were in the presence of a non-zero background B field,
That's what I was thinking,
Then,
yeah,
yeah,
because
then
black
that-
hole can have a.
Yeah.
Itself can have magnetic.
So that would be like some axion, like converting to a photon. right?
Yeah,
Mhm.
in the background of the B field.
Yeah, so people have actually studied that, and that again, like that process is one of FA suppressed, and FA is really large.
So you're just saying because one of FA,
Yeah.
it's a.
So like I look at your estimate for the B field, it's 10 to the 8 Gauss, right? Something like
Yeah.
that. So for this luminosity to be really high, it means this object is very puffy, like very extended,
Yeah,
right? So can you use like the tides, like the deformability of the tides to constrain these objects? Because
so can you say that?
so
I know
yeah,
deformation.
tidal, because like these objects, because they're like you said, they're very luminous, means they're very extended.
Yeah.
So I wonder how much energy of this object is stored in the atmosphere of this
Charge
object.
particle or?
Yeah, just because you're.
Yeah.
Because there's a nucleus, right, which is a black hole. It's like doesn't deform.
Yeah.
But there's a large magnetic field outside the nucleus, which can be deformed when you have
Right.
this in spiral, right? So I wonder whether you can extract some constraints on that just using the tides.
Yeah, so the answer is no, and the reason is the most of the energy density is in dark photon cloud, which itself is very rigid. Okay, the energy density that is actually stored in the visible electromagnetic field is order epsilon squared, which is roughly like 10⁻12 of the total mass. For these parameters that we're interested.
But you said the luminosity of this object is much larger, will be much larger than the pulsar, right? But the pulsar has a Gauss that could be as large as like 10 to the 15 Gauss. So
Yes.
I wonder why is your luminosity so much bigger than, say, a pulse? Like
Yeah, because it's large, right? Like the B field is uniform over a much larger size.
yeah. So the
In a
standard
pulsar, it's like 1 cubed decay.
So that's why I think it should be very extended, just in not just dark ones, but also the standard model.
Yeah, the standard model ones is also extended, but like the standard model ones compared to the dark ones only carry a very subcomponent of the energy. So gravitationally, like the standard model charge particle doesn't make.
There's not much energy in that part.
Huh?
There's not much mass like equivalence of energy in the B fields.
In the magnetic field, yeah.
So my question is somewhat silly, but is there, imagine that this vector bosons with these unusual properties of mass and epsilon exist, is there any motivation or anything to be learned from their existence? Then, apart from the fact that they exist, then, or what is the role in nature apart from giving us a signal of this crazy superradiance model?
Okay,
Or there is,
right.
there may be a way that you can motivate this. So in principle, you tell me these parameters, okay, these are crazy parameters, but
Yeah,
maybe
so,
but there is something to be learned.
That's a good question. Like, I think like, for that photon, there's no target. We don't know like what's the mass or what's the target. There's
Yeah.
no clear target for all over this parameter space. And it is just like a search you can do. Which.
But imagine we find it.
space which
Imagine that we finally learn.
Yeah.
What can we conclude from there? So
We'll
that-
see who ordered
eh?
it. We'll see who ordered it.
Yeah, well, this is a much stronger word than
No,
than
like,
the beyond.
exactly. I would have the same question, like, I don't know.
Is there something that we can use these photons for?
Is there something you can use this photon for? Like this mass is probably not.
Okay.
The 3 generations doesn't really serve that much purpose.
Yeah, those are crazy too.
Those are crazy. It's only create trouble for
The crazy
flavor
trouble.
physicists.
To see something, so like.
Yeah.
Okay, very good, very good. It's not an important question. Well, it is an important.
Is it,
question.
it's an important question, like, and, I think like it's, if like, if you ask me like, will I build something with that's like $10 million to look for this? No. But like, if we are looking for this, we are looking for this,
Million, I don't know. Okay,
maybe even less.
the unit is a million, so then I think it's okay.
No, it's okay,
Yeah.
very good, very good.
So if there is this heavy charge particle that has order one coupling to this vector boson, how heavy should it be to, not to affect this signal at all?
I think like the mass is roughly 10
Mm.
Because the density is roughly 10 MeV. Energy density.
So your claim is that this can be a lot brighter than a normal pulsar.
Yeah.
But, that's presumably a statement about epsilon. If I make epsilon a lot smaller, I can dial that. Right?
Yeah. So the power luminosity goes as epsilon squared. So for like a 10⁻⁷, you get like a 43 ergs per second. And then like if a normal pulsar is roughly like 10⁻32, 31. So you're talking about like 10⁻12 ish.
Could you use this type of mechanism to explain like some of these anomalous, like gamma ray burst observations and things like that that have
Yeah,
been
so like so in here, like we just
brighter than expected, like with the
Right.
mergers and things?
Right, so good question, like in this like work, like we just explored the dynamics in a very clean system. So and like in this system, we already see a lot of like sporadic emissions. So the one that I presented to you is the uniform emission. In principle, there can be X-ray flares, there can be fast Fourier bursts. This can be like the host of all of these phenomena. But like we haven't gotten to the point where we know how regular these things exist, what are the environment we need for these things to happen. We are looking at the system with a disk. The system gets much more complicated. But Niels is great, so he's making progress. Right, so it can be the host of a lot of these processes as well. Just we do not have like a very firm prediction on like what we actually see.
Great, let's thank Junwu again.
So Carlo.
I mean,